$5, but yeah, so, somebody's trying to do something. I mean, if you lost your thing, it's different.
Yeah, maybe you guys could talk
I'll show you. It's a new version of the old-fashioned. Instead of having.
How's it going, man? That's all right.
It's literally.
So is everything?
Everything's set up. You can like
The link probably is on the Houston School of AI on YouTube.
Okay.
yes.
How it's working.
Awesome.
So go ahead.
You know what? I have to run.
Yes,
from
you,
First.
yeah.
Finger. Touch it. And then that's it. Once you're logged in, it's a team. So I can log in.
Evan?
Yep. You can go whenever you're ready, John.
All right, everybody. Excuse me. Can I have everybody's attention, please, for a couple of minutes? So, thank you all for coming to today's class. This is going to be an extension of last week's class, and we're going to be looking at some more interesting features that we didn't get to, like transformers. So I'm going to be, just before I start the actual content material, I'll be doing some background work, such as posting the link to the YouTube Live, posting the link to the code, and posting the link to the websites that I'm going to reference.
See, one quick thing,
Yeah.
because I forgot to just remember this. Kelsey told me, you guys, you do have a computer, you have an evaluation for of the class, so you could give suggestions, things like that. There's on the Mac computers, so you have that.
Awesome. Thank you. So first, let's just do some, as I said, some housekeeping stuff. I just want to give a background note. Generally, every single one of our classes has a lot of code that we look through or do a code walkthrough. Today, just because the sheer weight of the content material, I think it's going to be like 95% content and maybe like 5% code, or if we even get there. But there'll be links for some programs which you can run in order to just cross-reference what I'm saying to actual live code samples. Okay, so first things first, I'm going to post a link of the website that I'm going to reference for the majority of this thing on the Houston School of AI website. So as I said, this one is really good because this actually visualizes everything. This guy's entire blog visualizes it. So if everybody could go to meetup.com and then go to today's meetup, this event, and yes, the YouTube Live link is there as posted by Vinicius, and you can click that. This is what we're going to be. This is one of the websites that I'm going to be using. As I get more and more into the content, I will post more and more links. And if we do get to the code, I just want to be ready for that. And that's essentially going to. That's going to just reference what we did last week, which was a lot of. There was just a lot of LSTMs and sequence-to-sequence stuff. So therefore, if you, the concepts between transformers and what we're going to learn today, both of them are kind of similar. So I'd like to just go over, use this as a notebook. And I will share that right now, which is NMT with detention. I'm going to share, this is actually adapted from TensorFlow's tutorials. So this is not my code, but however, they have put a lot of effort into making this very clean, and I will capitalize on that. So I'm going to put another link on the meetup, which has the code. Obviously, you can go over it in your free time, and or if we get to it at the end of class, and we can take care of it from there. And just obviously, every time we get a collab, I try to share it as a view-only mode. So then, if you want your own personal copy, you want to go to File and save a copy in Drive, and that'll make your own personal copy, which you can play around and just mess around with, and that won't affect the master copy. So that isn't a huge thing. It is not super important. The first thing first is we've had actually last week. If you take a look at the YouTube recording, we were enthusiastically going over some of the fundamental mathematics of the long short-term memory network, the LSTM. And I do see some new faces here. So briefly, like for like 5 to 6 minutes going to go over the RNN, then another 10 minutes LSTM, and then we're going to jump into sequence and transformer models in class. That's going to be the goal of the class. The goal of the class is explain attention, self-attention, transformer models, and give an insight into the future. Well, not really future, but more recent models like BERT, GPT, ERNIE, and these terms which are being thrown around the NLP field. Like what exactly do they mean? So quick RNN is very simple. It's just like RNNs are used for sequences. So what is a sequence? It's text, stocks, anything which is represented over time, or words as with reference to text. So essentially having it. I'm sorry, this mic is dead. But essentially for RNNs, which stand for recurrent neural networks, you have an input. Let's say like if that's the word, it passes through the main body, and over here we generate this thing called a hidden state. So I'm just call it 80, and then you generate an output. And this hidden state is kind of like our context of our entire sentence. So the hidden state has because let's say you're trying to understand the word that I'm currently saying. You won't really understand what I am saying without having reference to, I don't know, for the short term, let's just say like 20 or 30 words before. It won't make sense, right? Take any given word, like just the word word. If I say WORD, and I'm like, predict the sentiment of the word, like you don't exactly know it because it's only one individual token. You need to know the information, the context in which it was used. And for that comes the RNN, which is just essentially, it's just a very basic neural network which loops in over and over again. So this is, say, the first word, and this is the second word. I'm going to label words as T for time, and that's the word, and then the hidden state from the previous word, the context from the previous word, gets appended to the context of the current word, and then there's an output here. And essentially, it just loops on and on and on. Like you can essentially think of this as an infinite cycle. And any questions on RNNs? I'm not going to go into this in detail, but I can answer any high-level questions. Okay, so now let's think about this. If I'm reading whatever, Leo Tolstoy's, any one of his novels, right? They're all really, really big. And I'm talking about the main character, but the main character was introduced 500 pages ago. And you're looking at like tens of thousands of words. That's a lot of words. The problem with this is he doesn't remember the effect of the information from 100 or 1,000 years ago. It doesn't exactly pan out. Like you don't remember it. So if I wrote an essay, this model, it'll probably be effective for a very short span of text, like maybe like 2 sentences, paragraph, max. Like think of like a movie review size length, right? Or a tweet, like 250 characters or less. But we want information about all of the previous states, about all the previous words, and therefore there was a new model which was introduced, and that is called the long short-term memory network. Now the LSTM is really good because it has an intricate way of dealing with memory. So whatever hidden state that you see here, it selectively forgets and adds hidden state. So it selectively updates this in order to remember the right things. So now if I'm talking, English isn't the greatest example, but let's talk about a different language where gender is a really common thing, right? Almost all objects have gender. So when you're dealing with that scenario, you don't really need to know the gender of the subject from the previous sentence. It's not a huge deal. You don't need to worry about that too much. But you want to forget that, but you want to update that information with the current gender of the current sentence. And that's what the LSTM does. You can think about it as a T-shaped water pipe. So with 3 valves, right? So let's draw like a big T. So essentially how it works is you have at a high level, you have the input coming through, and say you have like a valve here. You have to forget. The order isn't exactly correct, but it gets the point through. And there's some memory here. All right, let's just put some blah 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 blah. There's some memory here. There's some memory here, and over here there's another valve, like over here. And this valve says I don't need this kind of information. The gender of the previous sentence, I don't really need it. This is learned exactly how much to let go. So this is like a number between 0 to 1, and which is I'm not going to forget any information or the valve is fully open, I don't want to remember anything. I'm just starting fresh. And it's never really those extremities. It's probably somewhere close to the middle. But some information is lost, and that's it. So maybe this part of the memory is gone because it said it doesn't matter to the context of the actual sentence. The gender of the previous sentence is a huge deal. That's what verbally. That's what you can say things. And there's a final valve here, which is more of a transformation feature, which essentially says how much do I want to output from my updated memory into my next LSTM. So now think a bunch of T-shaped valves like water pipes connected to each other in order to constantly update the information which is being learned, which is being forgotten, and which is being outputted. So that those 3-gate system is the LSTM. There have been updates to this called the gated return unit, and that's just a variation. And the GRU is just instead of 3 gates, it just scraps that. It's like, all right, let me just have 1 gate and let's just get cracking. I don't need multiple gates. And that's essentially the long short-term memory network. Any questions that I can go over this? Great. Okay, so now that we've revised, in a very brief span of time, what we were doing for the last 2 classes, and obviously if you have any specific questions, I'll put my email up at the end. Or actually, I'll just put it up right now. And if you have any specific questions, you can email me or watch the video of previous classes. And that should answer any questions because a lot of questions were brought up there. 11. Kachu, K-A-T-C-H-U, 11 @gmail.com. And I'll leave that there with you guys for the session. Okay, great. Now, last class we kind of talked about this thing called sequence-to-sequence networks, and we got some of the core idea down. We weren't able to flatten it out, but I think it's really important to go over that because the difference between the core part, which is going to be transformers, and sequence-to-sequence is a huge deal. So it's just a small feature that's being implemented, and but that's okay. For now, we're going to, again, this is going to probably take a bit longer. Sequence-to-sequence networks, I'll try to go for 10 to 15 minutes. Because I know some people are very eager for transformers, and it's a very interesting topic. Okay, let's talk about sequence networks. How would I translate English to French? I am good is English. Je suis bien, that's French. Now, in this case, you can do a one-to-one mapping, like a keyword mapping. So I have I. What is that? Let's open up the book. Let's go to I. I maps to je. Boom. There. I have am. Go to the book, am maps to sweet, and then the same for good. Good, go to the book, it maps to bien. That's great. But for like 3-word sentences. Now what if you're dealing with 20-word sentences, paragraphs? A lot more information. Over there, the issue becomes that the order of the words is not the same. Like if you take a really complicated sentence, it's not a one-to-one mapping. Like this location of the subject and the verbs all be different. There's so many ways to represent. There's so many ways to represent the same exact sentence. So that is a current problem we have at hand, and that is why we want to use this thing called a sequence-to-sequence model. Now let's just dissect the term. So there's a sequence, which is an input sequence. So we have our text in English. 2, so transforming it into our output sequence, which is going to be our text in French. At the most fundamental level, that's it. And you don't need to do. One interesting thing, though, that I didn't talk about that much last class, is that sequence models, they don't need to just work for text to text. I know somebody who's done text to SQL, the database querying language, and it's pretty interesting. Like you type in exactly what information you want to get, and that'll transform it into like the join and whatever commands that there are, and get that information from the database. So very user-friendly database. Another really common thing is image capture. So for like a minute, let's just think about an image, right? So let's say the image is, I don't know, this is really bad, but like 2x2 image. So I have 2 pixels here, like A, B, 1, 2. Technically, if you unwrap it, you get like A1, comma B1, comma A2, comma B2. These are our pixels. These are our pixel representation. I have this beautiful image, my 4-pixel image, and I want to write a caption for that. What does this 4-pixel image say? And for the sake of this demonstration, even though pixels are arbitrary values, let's just say the pixel is like, there's a curve here, there's a curve here, a curve here, curve here, And let's just say that looks like a ball, right? Whatever, that looks like a ball. I want to say this is a tennis ball. That's my output. So I have my input sequence of an image, and then I convert it into this latent space. So how this transformation actually works is, let's go back to the English-French example. I speak in English, but then I convert it into this, let's say, some hidden mysterious language X, right? And in language X, it's like an abstract representation of the words. And then I convert that abstract representation back into the words of another language. That's called a decoder. So we have our encoder. So let me, I'm sorry, I should have probably drawn this a bit more. But this is converted into, let's say, let's just call this language X some representation. And that's the one that I have, or it is a, let's just say that's what it is. So we have our encoder, we have our, for now, I'm going to call it latent space, right? Let's just call it latent space. There are many different words that go for this, and that's based on the context, and not the context, the use case which you use it. In image to text, it'll be latent space. In text to text, you can call it memory. I mean, they're all basically referring to the same thing, a more abstract version. And then that is decoded using this thing called a decoder, and boom, you get a caption. So there are many use cases, as I said, language to language, neural machine translation, image to text, image captioning. And there are a lot of, as I said, possibilities for this thing. I mean, how about using a caption generating image from that? So that's, whatever the brain can think of, you can do that. So that is a sequence-to-sequence network. I have an encoder, I'm converting it into an abstract version of text, and then I'm decoding it. Now, you can think of this as some sort of compression algorithm. Obviously, everybody's heard of zip files, etc. You can think about this as converting into a different variation of a zip file where the information doesn't always completely translate back. I'll tell you exactly what I mean. In the perfect ideal world, I'm translating the entirety. This actually happened. In Google Translate, you put Shakespeare, entirety of Shakespeare. You put that into Google Translate and you translate into like French or Spanish. I don't recall the language specifically. You take a Spanish translation, you put that back into Google Translate to translate back to English, and it gets a perfect copy. Now that's great. Like, it's done our job perfectly. And that is obviously very rare. And I wouldn't say rare, but very complicated to get to that level of perfect translation. But that's all based on how we encode it in our latent space here. That's a very, very important step. For this series is the NLP class. We're not doing image captioning, so this is just an intuitive example that I wanted to give you. But for the rest of this class, we are going to go back to textual examples. Okay, great. So an interesting way on how I'm going to take this class is I'm going to explain the concept of an architecture or a model or whatever, but then I'm going to explain its shortcomings and why they had to upgrade to a better and more intuitive architecture, so we can actually understand the progression as opposed to this exists, that exists, this exists. Like, why does that exist? How did that come into play? Okay, so let's go back to text. I am good. And to anybody who's bilingual, this should be like a joke, right? This is like, you're not even thinking about this. But how exactly do we represent that? So we have that goes to our, let's say, language X, and then it goes to our, sweet. For the encoder and decoder aspects, we can fundamentally think about it as an RNN, the recurrent neural network that I mentioned at the beginning of the class. With the input, the hidden state, the output, and hidden state is passed on as information as a context, right? So essentially, hidden state is generated. So you can think about how about this? So after each word, a hidden state is generated. So let's just take like a vector. That's a hidden state. This is a size that we can arbitrarily determine. It is a hyperparameter. We tune this how complicated we want the hidden state to be. And for those who may have not heard, hyperparameters are essentially things that you can tune in order to get the best results. Like the temperature, you want to feel the most comfortable. So in this case, how do we increase the accuracy with the tuning of the hyperparameters? So you have H0, hidden state 0. You have H1, which is just the same size vector, different numbers with the relation to this word. And then you finally have H2, which is another blah, blah, blah. And that is based off of this word and these words. So this is just solely based out of the first word, which is I. The hidden state generated for am is based out of am and the hidden state for I. The hidden state generated for good is based out of am and the hidden state for I is based on the previous information. So by that logic, we can show, okay, the last hidden state, what must that be? That must be a way of representing everything in the text. So this last vector, we can think about that, and don't worry about the technical term vector. Just think about it as a memory. This last, thing that we're getting, it's a representation of all the words that were before, and that's exactly what the hidden state is. And now by doing LSTMs, by doing more advanced architectures, you're just making this hidden state better and better and better. It's kind of the main goal. Okay, so before I go on to the, actually, you know what? I'll explain one more thing before I take questions. And for those who are wondering, how does it actually create that language X? That language X is actually this hidden state. This arbitrary this representation of the previous words is what is used as input to the decoder. So before I get to this part, any questions on exactly what the hidden state is and why it's exactly language X? And I can go over that. Any discrepancies. Awesome. Okay, great. That's so far so good. So we have our language X. Whoa, we got a context representation. Now what do we do with this? We want to decode it. I have I'm good. I have this some sort of n-dimensional representation of I am good. I am good is represented by 0.1, 0.5, whatever, some list of numbers. And now you want to decode it into the actual word. And this process is relatively simple. It's just, you have your hidden state. What is the first word that could come out of it? Let's see. What's the first word that could come out of it in French? And using this hidden state, you get je. Je is you just make a prediction, right? You have all the possible words, I am, je, blah, 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 whatever, infinite number of words, or how many ever you're setting. And you get your first word, je. Then you combine this hidden state with the hidden state generated by je, and then you create a new hidden state, which is what you use to predict the next word, which is sweet. And then you do the same information, you append this information, the information from je, the information from sweet, and you create the last representation, which would be yeah. So at the end of the day, through to summarize the sequence, you're essentially generating a contextualized representation of an input sequence. You're trying to make it in, what does that sentence mean at its core? And then you're using that in order to translate it back. And this is showing, whoa, we're getting a lot better results because of this. And it's great. So yeah, that is the encoder-decoder architecture for sequence to sequence. Fundamentally, that's what it works. Now we're going to get into attention, which is a very important and a heavy subject because, it's not too heavy, but I'd like to go over it a bit in detail. And I'll be sharing my screen for that. I have a visualization. But before I go, any questions on how sequence to sequence is, what the encoder is, what the decoder is, this hidden state that we're talking about, any terms that I can define?
You have hidden state for decoders. Why do you have your H1, H2? So for the decoder, you said we have J first, and then we next. So you have to.
Yeah, we have. I'm sorry, I should have illustrated that. So that's H3.
Makes sense. And my question is, last class you mentioned about actually the first have a vector there. So I would think H0 corresponding to I, and next corresponding to M, and then corresponding to H2, and then all of them has to decode at the same time, and now you have the picture of H2. So does that mean H2 include every information in that sentence or just the last word? And then when you do the H3 actually on decoder, and then H3 actually combine with the H1 on left. So generate the H2 on the right. So what that?
Great. You actually kind of described attention partially. The next topic that we're going to discuss, you kind of got there. But so that's good. No big deal. Yes, and so H2 is not the representation of good. H2 is the meaning of I am good. So H is the meaning of I, and H0 is the meaning of just the sentence at I. Think about it, not the word I, the sentence at I.
And one actually represent I am.
Yeah.
H two is
And to clarify, H1 or say H2, H2 is not H1 plus H0. It's not just you're adding them. It's a different exactly. It's a new hidden state altogether. That's what. Yeah, no worries. That's what that's it. Great question. So, any other question that I can answer about hidden states? We are great on track. 1 hour and we give our attention. Okay, so feel free to interrupt me if you want me to go into anything in detail a bit more, and I will be glad to do so. Everybody could just navigate to the link that I posted in the meetup, which is this blog post, and that let's do it another time. Okay, so visualizing in machine translation, and whatever I drew, it actually. If you can just give me 1 second, I'll pull it up on my. Okay, great. So whatever I drew, it does it a lot better. And essentially, this is a sequence-to-sequence model, like blah blah. You have your sequence. It's passed into, let's just say the hidden state or memory or whatever you want to call it, and that's outputting another sequence. And in the neural machine translation, same exact dealio, just V2DL, it's passed into the middle, and it's outputting I am a student, which is great. This is not really the videos that I'm trying to show. This is what context looks like. It's just the last hidden state of the model itself. This is the last one, say H2. And I was talking about how you can arbitrarily define it, and you can see here, it's not really a size 4. So the thing is, you want to depending on the complexity of your data, the complexity of your model, you want to make your architecture a bit more complex. What I mean by that is you're always trying to make things bigger and better. That's essentially it. And so the size would be 256 by 12 or 1024, which is the size of the memory. So we can encompass a good chunk of information without having too much. There is a limit. Like you can't do 10,000. It won't make sense. So we gotta have some sort of limit which prevents that. And that is great. Word embeddings, let's not worry about that too much right now. It's a way of encoding our data. And you can look to the first video for the class. I'm not gonna go over that today. RN, blah, blah, blah. I'll explain this. All right. So let's talk about this thing called attention. Attention is really important for transformers, but essentially, I want to pull up a diagram of attention. I hope let me pull this up. Actually, you can't see this, so let's just stick to this. Gosh. Yeah, okay, this is exactly what I'm trying to do here. And so essentially, attention is it's a way of not. The problem is, I told you, right? You can't. What if you have 10,000 words back? You're not really encoding that information. So attention, the key part is instead of just giving one hidden state, which is H3, the last one, you're giving all the hidden states together. That's what you're doing. And therefore, you're able to say, I don't really care about that word. You can think about it as a variation on, the whole memory aspect of the LSTM, such that you're trying to map a word to another word, not based off the entire context. So I'll try to elaborate a bit more on what I mean. So I'm creating H0, I'm creating H1, I'm creating H2. H2 is the H2 is the total representation of the sentence. And that is what I'm using to go and decode. Now, I'll tell you something. What if I gave you a long paragraph and I just ended it with the last word and said, translate the entire paragraph right now. Like read from you to order and then translate the entire thing. Doesn't really make sense. People generally, if it's a relatively short sentence, it should be fine. But when you're dealing with bigger sentences, you kind of want to chunk it bit by bit by bit. And you're like, okay, I want to translate this, then I want to translate that, then I want to translate this, then I want to translate that. It's like you want to translate chunks of the sentence together. And that is essentially what attention is all about. So basically, now that we have our last hidden state, there's a function. Now you can think to your question earlier. You can think of associating a hidden state with a word. I would say think about it as the influence that a word has put on the meaning of the sentence. I feel like that's a great way to think about it. The influence that a word has put on the meaning of the sentence. And for really important words, like trace back to what I said. The influence the word has put on the meaning of the entire sentence. And then the next thing you do is you have the scoring function. Now that you've tied the word to a hidden state, you've done that mapping, you have a score, which is like from 0 to 1, which is like, okay, that that word is really important to the context of the sentence. I want to attend to it, aka attention. And for the other words that don't really matter at all, I don't want to attend to it. So when you're looking at this 2D grid, you can see that the black ones are the ones that don't really matter to the, like when you do, this is attention. So we're not worried about the meaning of a word to a sentence too much, as opposed to the relation between two sequences. So you have your hidden state, and then accord stands with agreement, sur stands with on, like it makes sense. It's a mapping, but in a weirder way than it is a book-to-book mapping. So you're not having a book and looking through the book. It's just that you're saying, in order to determine the translation of the word the, like sur is, which is literally translates to on or whatever, that is the most close hidden state. That's the hidden state which matters the most while determining the information. And you know what I was telling about earlier, when it's not really a one-to-one translation, you can just change the words to each other. It's super representative here because it's like zone economic European, and over here it's European economic area. Like area, which is the last word, is zone for the first word. Therefore, like you see, this is the grid. As opposed to it being a straight line, like it coming down. The problem is that like these two different things are in different orders. Therefore, the structural orders of this are different, and this is one of the main reasons of attention. Okay, so let me.
So what's the shade difference? What does that mean? Like some are wider than some are gray.
That means it's the most important to the while translating, while doing between two sequences. That means it matters the most in. So essentially, the word economy best associates with economic in the given context. So the word zone doesn't really matter to European. Like, say this is our entire dictionary, right, of all the possible words we could have. The word that matches, let me talk in plain English. The word that matters the most for any sentence that I'm saying, say I have the word it or whatever, based off of the context, it is representing whatever the associated word in a different language. So based off the context, which word makes the most sense? I'll tell you exactly what I mean. In word vectors, the word bank, right? Word vector is something we talked about earlier. The word bank has the same or stick, right? It has the same representation regardless of the context used. So let's stick to the plan, and versus I picked a stick from the ground. Stick has the same meaning. What attention does is, based off of the context of the previous words, stick best translates to the, let's just say, like stay, right? Stick best translates to stay based off of the given context. And in a different context, so if perhaps it was let's pick up the, and this one was stick. Stick would best associate with what's called like actual like a twig or a tree, a branch or something. So it's based on the context, what word does it most associate with? That's what the white lines mean. The wider it is, the more association there is between the words. The darker it is, the less association there is between the words.
So like one word can be associated. So one word can be associated with several other words.
Yeah, it can.
So like area has like zone and economic.
Yeah, exactly. So I don't know if you can see this in the back.
Whatever.
Right. So I don't know if you can see this in the back, but this is partially shaded in different spots. Let's just say this is a word, not the period or full stop or whatever. Let's just say it was a word. It just means that it could represent, like the mappings could exist for different words. Like the agreement on the European zone area, the period could be after area. That's essentially kind of what it's saying. Like the association between what the sentence would have ended there. All it's saying is that I have two sentences based off of the context. Which word does it go? Which word does it associate with in the final output? Does that make a bit more sense is what I'm saying? Or would you like me to illustrate it and draw it out? Okay, I should probably repeat it. I think I understand what it is. All right, how about this? Let me see if they have any more diagrams here, which I think they should have one. Let's take a look at the end of the video. Essentially, they're based on the context. So I've said 1,000 words before. Based off of this context, je means I. That's it. I, je. Je could mean I am a, but based off my current hidden state, which represents the context, it means I. Now, suis, based off the hidden state or the context of both je and suis, it could represent many different things. It could represent right? But it most likely represents am. Now, when I have the final word, étudiant, across, well, I mean, this is not really the word transition, but if I have the word étudiant, it looks through all the hidden states, the final hidden state, and it's like, based on this entire sentence, the context, the word étudiant, based off of je and suis, it most likely means student. I mean, if you go to the end of the video, it'll say student here. So, based off of the previous context, what word can I associate it with, essentially? Does that make a bit more sense? Yeah, of course. Any other questions on this? For me personally, self-attention, which is what we're going to be talking about next, I don't know, maybe like 20, 15 minutes, is a bit easier to understand than attention itself. But it is very important to understand what this means. It's just dynamically associating meaning, because the meaning changes based off the hidden state vector. Okay. Any more questions? Yes.
Does it always go as far back as the beginning of the sentence? Say if you have a long sentence.
It depends. Yeah, it depends on the input sequence. So however far you feed in your input sequence, it'll go that far.
So that's something to define.
Yeah, exactly. And oh well, I can't find it, but that's okay. Okay. Any other questions that I can answer on attention? Okay.
I didn't read the entire slide there, but I noticed quickly that in the translation you have je suis étudiant and je suis un étudiant. So where did it make that correction? Because in the example you have the two translation.
I'm so sorry, I didn't hear you. Or I can scroll up.
Well, it changes the context. So like in this example, your translation is je suis étudiant, which I guess is, possible as an answer. And then some of the other example, if you scroll up and down, you have a translation of je suis un étudiant. So it made some correction there in between like different steps.
Yes, which example? I mean, the answer is not too fancy. It's just that, okay, I couldn't find the example, but that's okay. I'll give you the answer. It's just based on the sequence. For that particular example, like the two examples are different. It's not like a stuff.
Okay, it's
It
not
doesn't
like
add and. It's just,
okay.
When I was translating, I just put just Van and Julia.
Okay, I thought it was like a process.
Oh yeah, no, great question. Yeah, it is not a process. Sorry for the misunderstanding. Okay, anything else? This is neural machine translation, and this is what actually is represented in this notebook, this perfect TensorFlow 2.0 notebook. This is another interesting issue, visualization. In fact, these are the essential weights that I was talking about, like based on the hidden state, which hidden state matters the most while representing the word. And you finally get this context vector, and then what you do is you kind of multiply the hidden state by the, so think about it as different dials, right? I have 5 different dials from 0 to 1, or how many ever the words are, how many ever the number of words are. And I'm like, okay, for this word, based off of the previous context, most likely associates with this other word. And if you gave no context at all, the answer could be different. It's just based on the context you have different things. Now let's think about a great problem. Let's answer 2 different questions with this. Essentially, one main question is that it's a probability distribution. So exactly how would you calculate? Okay, this is more of a technical thing, but how would you calculate the loss? How would you exactly treat this? And a fundamental way to calculate the loss of a probability distribution is you just subtract the confidences across each one. So say I have a number of classes, like 15 classes, and I have different scores for all of them. I'm just essentially I'm just going to subtract the ideal score as opposed to the non-ideal score. And I'll kind of show what I mean by that. So can I erase this? Anybody would like to reference the material? So a lot of machine learning always boils down. I mean, in my personal opinion, you don't really need to worry about architecture that much. I mean, that's in later stages. In the beginning, you're worrying about, in order to even get it run, how does your input look like, how does your output look like, and how are you training the model? How's the loss look like? That's the three main aspects. But okay, so it's creating a probability. It's called a language model. Now that we have these attention weights, we are able to generate the meaning of a word based off of different contexts. Everybody's on the same page. Through attention, we're able to generate different meanings of the word based off the context. Now through that, now we're eradicating word vectors. I mean, we're not eradicating it, but you still need it for some steps. But we're creating a way better representation of the word. Stick now is different. The representation of stick, the matrix which represents stick, is different based off the context. It's not anymore based off of just in some sort of 2D mapping. The word stick is 1, 1. It's not static. It's dynamic based off the context. That's the flavor attention brings in, and that's why we're able to make this language model so much better, because we're able to change the context of the word, the meaning of the word based on the context. That is a key takeaway. Attention, meaning of the word based on context. Another problem is the loss, which I mentioned earlier, and essentially it's a probability distribution. So mathematically, all you need to do is you need to find the difference in the outputs that is generated. So if it's supposed to generate, let's see, back to the old example. And then the possible options were like I mean, okay, you know what? For the sake of meaning, I'm going to jumble this up. Am I student? The correct answer for what this word A2 should translate to is student. So if we do a one-hot encoding, one-hot encoding is essentially you have multiple switches. So each word is represented by either a 0 or a 1. And if I want to represent the word I, it'll be 0, 0, 1, so I'm turning the switch on, and 0. So the ideal, I can answer any more questions about that later, but I want to get this point. So the ideal representation would be 0, 0, 0, 1 for student, that's A2D student. But what if the model gets something like 0, 1, 0, 0? Essentially, you can find the difference by just subtracting the two probability distributions, and that is one possible way of doing it. And in that case, you can just get how far off it was from the right answer. There are also things like categorical cross entropy and other loss functions. But for now, you don't need to worry about it too much. I mean, it is the last class, so I'm not going to say we can explain it in the next class. But if we have time at the end, because I really want to get to transformers, then I will go over the equations. And if you're so particularly inclined, go ahead and look at these equations. And I'm not going to lie to you, I can't exactly answer what each and everything means. You've got to have to give a minute to just associate the variables. But in your own free time, if you would specifically like to, you can take a look at this notebook. Okay, now that we're done with neural machine translation, with attention. Great. Actually, I think this representation is really good. I want to show this visualization. Is it this one? It is this one. All right. You have your hidden states, and then you have a score. You don't need to really worry about the scoring function. It's just an attention value that's given. These two steps, I'm just going to combine it and say these are the different dials, how important we want to care about this. And then so we're multiplying essentially the attention vector by the softmax scores, and then we get that this word is the most important. This hidden state makes the most sense, and therefore we get a final answer of our context vector at our time step. It's essentially a representation of what I said. If some specific things don't make sense here, don't worry about it. What I explained earlier was a general concept, so it encompasses this entire thing. Now I want to move on to transformers, and as I mentioned earlier, I want to share another link. So I found out about this blog, I think like 2 days ago. So I actually genuinely love it because it makes a lot of sense and it's really good for teaching. So on the meetup, I am going to post another link. Illustrated transformer. So we'll give 2 minutes for everybody to do that. And, I really want to pull up a visualization, but I'm just going to do a walkthrough of this. All right. Okay, so now that everybody's on here, and is anybody having trouble finding this? Sure, go back. Okay. So transformer, whatever you can. It's just about the transformer, like the TV show or the movie series, whatever. That's why it has these hot red flames. That's okay. So transformer fundamentally, very, very, not even very. Like I want to say like the same thing. I want to go a seventh thing. Very, very similar, such that you have a input. You have an encoder, you have a decoder, and you have your output. Same thing, we've seen this already. It's just a sequence-to-sequence network. But transformers go crazy in that they have 6 encoders and 6 decoders. What? How does that make sense? You have your input, and you can think about this as, okay, I mean, we learned about this in like 5th grade science, but it's like sedimentation, like filtration to sedimentation. Whatever. I think is that whatever it says. Yeah, let's go with that. This is a decently. This makes so much sense. Basically, what's happening here is that you've heard of how you can take dirty water, not dirty, like I mean you're gonna have the germs there, but you have some more dirt and rocks in the water. You pass it through layers of like rocks, and that's why groundwater is so fresh, right? You can drink groundwater because it's passed through tons of filtration. Essentially, what we're doing with transformers here, we're filtering the words and extracting the context. So now I'll tell you why it goes crazy. Well, before that, let's think about this for a second. Sorry. Oops. In our classical encoder, what do we have? We have one encoder. We get attention for different translations, and we're essentially able to say, okay, this word based off the context most associates with this other word. That's how we're translating. But if you abstract it, we're talking words. Just trying to make this as general and in English as possible. But if you take a look at the mathematical operations, each input is represented by a vector. That's it. Okay, vector is just a one-dimensional matrix. Like the dot thing that I drew for the density, that's a vector. For the encoder, it doesn't care what the previous thing is. It doesn't even know it's a vector. Like what is it? It's just a series of numbers to it. So you're passing in the same vector, not the same vector, the same size vector over and over and over and over and over again. So you're continuously filtering it. So as opposed to just taking one shot in the hidden states, like you see it and then you're done, it's going through it 6 different times. And now it says in the article itself, but there's nothing crazy about the number 6. It's just that it's a hyperparameter, so you can add some more blocks, you can take some more blocks out, and it works great. I'll tell you another reason why we want this transformer. Sorry, I should have mentioned this a bit earlier. I lost track of thoughts. But we have all this great machinery, hardware, GPUs, TPUs. Really cool things that you can't run a neural network on a CPU, like an advanced one, and really expect to get results, in this year, to be honest, in like a decade. Just kidding, it's probably going to take some time. But the thing with attention is that it's able to parallelize it. What does parallelize mean? It's GPUs focus on distributed learning. Now, I'm going to explain why exactly it's able to parallelize this training, but it's able to split the training up into a broader step so you can optimize the computation. So this gets better results in faster times. That's what everybody wants to hear. And, that's why I would like this is like the seminal paper of the field because So many models have been, brought up because of this. But anyway, back to the main part. There's an encoder. There's a word of some size vector. It's going through the encoder. It's using the hidden states. It's mapping all the, it's mapping it. Let's not say another word. It's mapping it to another vector. And then that vector is passed this into the encoder. That's passing into this encoder. That's what it's Now, at the end of the encoder, you just have a really, really fancy representation of what was originally here. Now, you're like, okay, so now that I have such a representation, what exactly do you want to do to it? And this essentially is this final representation, this final encoded representation of that word. So let's just say this was a one-word sentence, right? Let's ignore I am a student. Let's just say it was a one-word sentence. This final representation of this word is then given to the decoders, which then are able to at different time steps or at different hidden states are able to generate I'm a student. So what exactly do I need here? You use 6 encoders, you do a lot of filtration, then you use 6 decoders, and you just give the output. There's nothing really fancy that goes on with it by the whole, it's a stacking, like, you know how we have multiple convolutional neural network layers? Essentially a very, very similar concept. If you don't know what a CNN is, don't worry about it. It's just it'll just make the model more complicated. Sometimes more than it needs to be, but oftentimes it's exactly it. Okay. Any questions about why we have 6 different blocks? We can call them encoding blocks. So you know how I mentioned earlier in the class, everything is based on how complicated you have, how complicated your model is, how complicated your data is. When you are fitting with a data such as the English language, you're essentially able to, you want it to be pretty complicated in order to properly understand everything. Therefore, you're just adding a lot. And this isn't even the end of it. We have this thing called multi-headed attention. You're like, what? What's multi-headed attention? That's just an even more, it's like adding like a cherry on top on how complicated this model gets. It gets really complicated. Not to explain, it's just in the number of quality that it has. Okay, so let's take a look at the next thing here. All right, so each encoder block is represented as 2 different aspects, which you have your self-attention and your feed-forward neural network. So let's take a minute, let's pause, let's talk about self-attention. So everybody's heard of attention, we just talked about it 20 minutes ago. Self-attention says, okay, I really want to explain this. I hope they have a diagram. That's okay. Self-attention, just give me half a second. Okay. You don't worry about these different colors, etc. Just think about this as one color. Self-attention is really cool because it does, in the previous attention example, we have a different language, English, and we have a different language, French. Through self-attention, you're basically able to say, let me take a look at my own sentence and let me see what word is important. What word matters with context to all the previous words? So let's take this example, the animal didn't cross the street because it was too tired. Also, I will explain this whole underscore thing just in a minute, but for now, let's leave it. The animal didn't cross the street because it was too tired. What does it represent? What does this it represent? We know that it represents an animal, right? That's as human beings we understand. But through self-attention, which is learned, we're able to say, whoa, the it actually represents the animal right here, this content, this representation over here. And that's what, through self-attention, as in like looking what word matters based off of the context of the previous word, we can generate our final example. Now, before I go on, logically, if you think about it, if I'm trying to find exactly what word matters for the context of it, won't it just refer back to the sentence it? I think I'd like to draw this for a second. This is too long of a sentence. I'll just draw this. But let's just say the animal didn't cross the street. Didn't cross the street. Okay, sorry, that was probably not good spacing. But I'm just going to put the first letter. The animal didn't cross the street because it was too tired. I'll just write it. This is a triangle. And the animal didn't cross the street because it was. In our previous attention, we had different languages. Sorry, there should be a T here, and then you should have like what's it called again? A heat map, essentially. If you're asking what word in this previous sentence matters the most to it, it'll directly lead you to the word it in the other sentence. So if you logically think about it, I'm asking what word matters the most to the context of that word. Like, is everybody able to follow along with what I'm saying? If I'm asking what word matters the most to the context of it, it'll just mirror back. It'll say it matters the most to the context of it. Can everybody follow along with what I'm saying? I know it's kind of weird in the language. If you have any questions, please feel free to stop me. I'll be glad to go over this a couple of times.
What does the color do?
Color, you can think about as the importance that it's giving to a particular word.
So darker is more important.
The darker, yeah, exactly. So it represents animal, essentially. That's the animal.
Does the darker correspond to the attention weights?
Yeah, the darker corresponds, exactly. The darker corresponds to attention weights of the given word.
So the attention weights are like, I'm sorry, I'm using an economics term, like a logistic function of all the vast hidden states.
Yeah.
It takes the score or whatever that raw number is, takes the sum, divides each score by that
Absolutely.
sum, normalizes it. That's
Exactly.
the
It's
softmax,
just
right?
normalization.
Yeah.
So,
So it
it's like,
sums to 1.
yeah, exactly.
Yeah,
So
okay.
all the attention of all this comes to 1. That's
Yeah.
what anything is. So essentially now you want to ignore the same. If I'm asking for the context of a word in a sentence, that word is going to be reflected. But I don't care about it. I don't want, that's like writing the question as the answer on the test. It doesn't make sense. I want to get animal, I want to get duck, I want to get whatever other words that I want to get. And through that, essentially, that's where self-attention, whatever what I've been saying, comes into play. So it reflects back on, it identifies which word matters the most in an algorithm similar to the original attention that is explained in detail here. Actually, you know what? After I'm done with this, I'm going to go over a bit of a technical definition of it. But if my words were probably pretty weird to understand, this paragraph kind of explains it a bit easier. But that's okay. Let's go back to this. That's not complicated, right? And okay, so we have the encoder's inputs first. Here, the encoder's inputs first go to the self-attention layer, which does exactly what I'm saying. Now, this feed-forward neural network, this is the key. This is like, how do you say this? The cherry on top. Because the feed-forward neural network is what enables parallelization. So this is a hefty topic, so I'm going to take a couple minutes and dissect this. I have self-attention here. That's great. And that is able to, you can't parallelize this exactly, but you can parallelize this. This feed-forward neural network is not something fancy that we need to worry about. It's just for the sake of processing of the vectors. It's like a non-linearization tool, and don't really worry about the meaning too much. It's just a necessary step that we need to do in order to get this data up and running. Whatever we have from, we can't really feed our self-attention directly. We need to have some sort of pre-processing step. It's non-linear. So now this part is what's going to be able to parallelize, because this doesn't care what the other words were. Self-attention is the one that cares what the previous words were, the future words were, whatever. That's what self-attention cares about. The feed-forward neural network doesn't care about that. It just has this output and needs to transform it. And the matrix, which is going to transform it by, is going to be learned while training. So while training, you're going to learn this and exactly how to encode it and decode it, etc. All going to be learned by training. So you just get a word. Let me rephrase. You get a vector. You look at which other vectors matter the most. You feed that. You do some sort of nonlinearity transformation. You output it in the next step, and then you keep doing that. And since this doesn't matter for the other words, since it's just a transformation, this can be parallelized. This operation, it's at the end of the day, it's still a neural network. You're going to have like 100,000 parameters to make it. You're trying to get the best transformation possible. So you want to parallelize this operation. You don't want to waste computational resources. And therefore, that's why transformers are really good in using the most of the memory that you have, because it's able to split the task up into better representations. Does self-attention make sense so far? It's very similar to attention. So if I can field any questions. Yes, go ahead.
Well, just to kind of track what data is in these arrows. So you're coming in with like a sequence of words. Each word is a vector. And then self-attention creates a mapping from each word to a probability distribution over all of the other words in the sequence.
Yeah.
So then what's fed into the next step? Like,
Are you talking about this arrow or
yes,
that arrow?
yeah, the middle arrow.
This is just the outputs of the self-attention. It's just like which words to focus on. That's essentially all that's outputted by self-attention. It's like a matrix, whatever you said earlier, with like the probability distribution of the different words is what's outputted here. That, essentially, you can't directly feed that into the next encoder. So we need to do some sort of transformation with the matrix. So I'm not sure how exactly to answer your question, but I think all I can say is that for numerical computation reasons, you can't cut this as the output. You got to do some transformation and then pass that.
So like if you have an n-word sentence, you have n vectors going into self-attention.
Yeah.
And then you have an n by n, or you have n by n matrices coming out. Is that?
Okay, great question. Okay, so this is just one word that's passing through. It's not the entire sentence. Like, this self-attention is dependent on the other words as well. You're correct, but this arrow just represents one word, just one individual word being passed through.
Okay.
So therefore, I mean, if only one word is being passed through, you're finding the importance of the other words as well. You want to filter that back into another vector that can be passed through at the end. So it's essentially, in order to keep the sizes the same, you have to do an input-output mapping. And you want to best learn that input-output mapping. Because why can't we just use a matrix that we won't define ourselves in order to change the size? How then becomes different sentences are different, right? You can't have the same sentence, like the same knowledge and the same sentence applied to a completely different use. You can't apply English to French. That doesn't make sense. You need something which is focused, domain focused on just English or whatever. I think I want to do a bit more research on your question, get back to you to give a more comprehensive answer with the exact matrices that are going through. I will get back to your question. Thank you.
Yeah, my question was just that. So it's outputting one word at a time, as opposed to a vector output.
I think.
Or it doesn't really matter. My point was simply that the weights are going to change
Yeah.
the numbers that come out
Yeah.
of the previous layer. Just like an LSTM
Yeah.
uses the forget gate
Yeah.
to go back in history and provide some importance to the history without mapping the entire history.
Yeah, essentially, yeah. It's
Yeah,
literally just
okay.
the LSTM thing. And,
Doesn't answer your question exactly.
yeah, and obviously, I'm sorry. I wanted to look. The same thing happened last class as well with the LSTM, with the mathematics behind it. And I think since it's the last class, I can't really say I'm going to come to the next class. But I will send you an email. We'll just talk offline and we'll connect, and I'll give a better response to your question. I'm sorry for that. Okay, great. Essentially, let's take a look at the next step. So we have all these stacks of encoders, and you have like, whoa, a really cool representation. And I would like to specify that please, for the sake of the next part that we're going to talk about quickly after this, start to compartmentalize your thinking. Don't think of encoders and decoders as go hand in hand. It could also be that encoders are a separate bit and decoders are a separate bit. They don't need to be paired together. And that'll make a lot more sense in the future, like in the next 10 minutes. But for now, let's not worry about it. I'm going to go to the decoder step. Decoder step is very, very similar to the encoder step. It's the exact same thing. But however, there's a encoder. Now that you're actually translating it, you have to have another sentence. Like now, this is just attention, like back in the sequence model that we talked about. You have sentence A in English, you have sentence B in French. You just want to do the mapping and find what exactly matters. I'm not going to go over that too much. We talked about that in detail 20 minutes ago. So that's what encoder-decoder attention is. Okay, self-attention. 6 blocks of encoders. Sorry. I don't want to start to open up this question before I talk a bit more. There is something called multi-headed attention, which essentially takes regular attention and it goes crazy with it. And you get. I'm sorry, but this part, this represents the mathematics behind the calculation of self-attention in a really good way. And that's essentially like the best way it captures the information to answer your like what's being passed is just a sum of the outputs from all the different heads of attention. But you don't need to worry about that too much because you can read this. This represents in like plain English, like nothing too fancy. And where's this stuff? Okay, let's just take this. There's also this thing called multi-headed attention. Yes, there we go. Multi-headed attention is interesting because essentially you're taking regular attention and you're just dialing it up a notch, like a big chunk. And like computationally, we don't need to worry about it too much because it's mathematically it's not too different. It's just that you're having 8 copies of the same thing. So you know how we have 6 blocks of encoding and 6 blocks of decoding. Instead of that, we have just like 8 heads of attention, which essentially help out in deciding exactly what word matters the most. That's okay. That's just multi-headed attention. In the next 15 minutes, I would like to talk about the most recent advances in NLP. I'm probably not going to go into technical detail. I want to do an overview so you just are equipped with the knowledge that you can search up later on. And one key thing is that if you scroll all the way to the bottom of this, you have all these great resources that are like really helpful in order to understand everything that I'm saying in detail. There are lectures, there are Colab notebooks, other stuff like that. So you can take a look at that at your own free time. So before I start on BERT and earning, anything on transformers that I can answer to the best of my ability. So everybody's comfortable with transformers? Yes.
What are the major use cases of this besides translation?
One thing would be something that I mentioned earlier, which is image captioning, would be very important. There's another thing which is called language modeling, which is we're going to build into that. So transformers as a whole aren't used that much anymore. It's more than it's split in half. The encoders are different and the decoders are different. So all they do is, I guess this segues into my next topic. The encoders, the use of transformers would be to generate really good language models, to generate really good representations of the word. So, in old neural networks, okay, I'm not going to say old, they're so relatively new. We'd have a word vector embedding, and then we just do a classification based on the word vector. We have like an LSTM, we have an RN, we do a classification of the word vector embedding. And here, using this transformer approach, or the encoder approach, you're able to generate a really good representation of the word. Like you're able to say, it actually represents animal, and this is what the entire sentence means, or whatever I was talking about earlier, through attention. And you just had one layer of just a softmax layer, or with just one weight matrix being calculated. So because this is so good, you don't need to invest more resources later on down the line.
So you mean it is more efficient compared to the previous approaches?
Yeah, that's what I'd say. Exactly. I mean, the sizes, however, are incredibly huge. One trained model of BERT. So let me talk about BERT. BERT is one of the things that I am a lot more comfortable with. I've worked with that for a couple months. So BERT is bidirectional encoding representing transformers, whatever. It's a weird name. The name is wrong. Like I can say like pretty clearly that the name is wrong. And I think they just did it to associate with Muppets characters, but it's really stupid. But that's okay. They're really confusing the people by naming it. BERT, essentially, it's half of the transformer. I have the encoder, I have the decoder, I'm splitting it in half. I'm just passing in data through the encoder, I'm at stage 6, and I have a hidden state. So not hidden state, sorry. You have a final contextualized representation of the word. And BERT says, you take this representation, close your eyes, and you're done with your model. You have such a good representation that you just need to add one sort of, like based on different tasks. So there are many tasks in natural language processing. The couple would be single sentence classification. I'm trying to find the sentiment of a movie. I have 2 sentence classification. I have, I am going to the mall and I am going shopping. They're 2 different sentences. Do they mean the same exact thing? I have, next sentence prediction, or there's some other tasks. But essentially, I'll tell you another reason why this is very used, because it's very versatile. You're able to adapt this BERT model to any use case that you want, because the key is it's not doing the downstream task. It's taking off the downstream task from its approach. It's just saying, I don't care what use case you apply this word to. The fact is you have a really good representation of this word. Now do whatever you want with it. Whether you want to compare 2 different sentences, whether you want to compare in one sentence as a whole, it gives you that freedom and that versatility, which is why BERT is really, really good. It's heavy, but it's versatile. That's the thing. Now back to BERT. BERT just you have your final representation of the word here, and I just had to have a softmax or like some final layer that I have, depending on the task I can do it. And now I've talked about theory a lot. I want to talk about some more real world stuff. So BERT itself is trained off of 3.5 billion words, I think, or something in the billions of words from Wikipedia and Google Books. But when I am applying it in a say like a finance domain, right? I want to pull up a graph actually. I'll pull that up soon. But when you're applying it to the finance domain, the lingo use doesn't really apply to some whatever other option that I'm doing. Like general English doesn't make sense for the finance domain. So if I am trying to predict, so let's take a science thing, right? There's this popular data set called SciTail, which is by Allen Institute of Artificial Intelligence. And SciTail essentially says, I have different scientific sentences. Do they mean the same thing or are they contradicting? Now, BERT gets a 50% accuracy on that, literally random accuracy, because it's so bad, it doesn't understand the scientific lingo of it. So therefore, we use this really popular thing called fine-tuning, and we have more data and of a given domain and a given task, and we're able to dynamically fine-tune the representations of this original model. So whatever output that you get here, this took like 8 GPUs and like hundreds of hours, or I'm sorry, I don't know the exact amount, but it took a lot of memory to do. Nobody has a computational resource to create a BERT model for different domains. This is too expensive. So essentially you have some more data. All you have to do is you have the softmax there, and then you have this weight matrix. So let's take the math out of it. Essentially there's some sort of transformation which maps this representation into a class. That's all it does. And the softmax layer, the thing is you have to tune all these parameters to the data that you have. I have science data, I want to tune all of it to science data. Now, let's think about this. I like to call this controlled overfitting, because the whole point of overfitting is focusing on a specific aspect. Like your BERT is super general, but we want to overfit on the science domain. Now, what does that mean? If I give information from a finance domain, it's going to do work. It's going to do really bad. It's going to, like the accuracy will be really, really low, but it's going to do really good for one specific domain. So we have this really heavy model, 3.5 billion words, 300 million parameters, and we're like, just take this data and just be a bit better at it. I want you to be a bit more specific. It says, okay, I'll take the data, I'll train my parameters, I'll fine tune it to this specific domain, and then you get your own BERT model, which you can use with a lower computational cost than creating it yourself. And now that accuracy, the more data you have, the better it is, and you're getting like record levels of accuracy. This data set called the blue data set, you get 95% accuracy, you get 96% accuracy, whatever, you get really high accuracies. And that's essentially BERT. There's also other things like GPT, which is generative pre-trained transformer, and ERNIE, and stuff like that. And so if BERT is the encoder of the word, encoder aspect of the transformer, GPT is kind of like the decoder aspect of the transformer. Given some sort of input sequence, it can start generating super long sequences of text. And I'd like to demonstrate this real quick. So BERT is by Google, GPT is by OpenAI, ERNIE, I think ERNIE is by Baidu, the Chinese AI company, and there's some ULM fit as well. Those are the most common word is BERT, then it's a GPT-2, and there's some other things. I'll talk about the misnomer of BERT later, actually, that's very interesting. But if you could all go to OpenAI GPT-2, you're gonna like be stunned on how crazy it is. And my personal opinion, I mean, we are live streaming, but my personal opinion is that a lot of the creativity has been dwindling bit by bit in the field, because originally there was a lot of creativity such that like the research was generally intensive. But GPT-2 and GPT, it's literally 10 times the data and 10 times the size of the model. There's no innovation there. It's just overcomplicating it. So, but that's okay. I mean, I guess that's how stuff is. But you can take a look at this prompt, right? You're given a prompt. I think it's called interactive text generation. I don't really remember the exact technical term for this. But you're given, in a shocking finding, scientists discovered a herd of unicorns living in a remote, previously unexplored valley in the Andes Mountains. Even more surprising to the researcher was the fact that the unicorns spoke perfect English. What? So, how to read this? This is generated by the machine. The scientist named the population after the distinctive horn of its unicorn. These 4 horns, silver white unicorns, were previously unknown to science. And you can take your couple of minutes and read the entire thing later on. But it's absolutely fascinating. But they, now just a bit of like social commentary. This model is 1.5 billion parameters. To put that into perspective, BERT is 330 billion parameters. Now, if you up it up, if you up the quality, the number of parameters, and the amount of data that you use to train on, you're going to get better results, obviously. But they, however, think it's a security risk to release the 1.5 billion parameters model because it can generate text uncannily to a human. So they're doing some sort of controlled releases program. And whatever, that's not technical, but I thought it'd just be a tidbit that you'd like to know. So these are the language models that we have, and GPT-2 is absolutely amazing. And these are used greatly. Now, a bit more technical details. We've talked about the different language models, which are really common in today's day and age. Now, there are some aspects to it. So when you're fine-tuning, you have that softmax. You're fine-tuning, and this is just research talk, so you can close your computer to whatever you want to do. But when you're fine-tuning to a specific domain, you're also fine-tuning to a specific task. That BERT model that I talked here, it's not a science BERT model. It's a science BERT model which is focused on just predicting whether 2 scientific sentences mean the same. That's it in a story. That's what BERT does. I mean, if you want a different science model, which is trained for multiple tasks at the same time, so like the same model. So say in a scientific inquiry, you want to say 2 different sentences. Do they mean the same thing? You also want to say, given a single sentence, I don't know, is this like a scientifically valid thesis or something? Like you have some the science aspects still exist, but the tasks differ. Therefore, there's this aspect called multitask learning. So you can search up multitask task deep neural network. Oh, sorry, that's a GitHub page. Multitask deep neural network for natural language understanding. And whenever that loads, which is currently doing, this says I'm going to train while combining all the different tasks. I'm going to combine the single sentence, the dual sentence, the question answering, and the relevance ranking, whatever the 4 different tasks are. And it's going to combine all of them into training it, so you get better representations of the word. That's what it's saying. So at the end of the day, I don't have a BERT model focused for just scientific. I don't have a BERT model focused for just single sentence classification. I have a science BERT model, a BERT model focused for science, and a BERT model focused for financial technology, which you can use for different tasks. And that's great. So I'm going to fill a couple questions, and then I want to just add some closing thoughts about this session and something else. But other than that, actually, before I fill the questions, I'll tell you why BERT is a misnomer. Because BERT is bidirectional. So this is actually a relatively important concept. So how are LSTMs? LSTMs, everybody's heard. We didn't talk about them. Bidirectional LSTMs. I unfortunately didn't get it covered in this class, in this series. But essentially, RNNs, they look at, like, so blah, 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 let's say I am good. It looks at only the past in order to generate a representation. What if you take a look at the future as well? I am good because I saw my friends or something, right? In order to generate a better representation for the word good, you're able to look at, the past and the future in order to generate a representation. That's what bidirectional means. And Google's isn't bidirectional. It's not like they're looking at the past and the future. What they're doing is they're feeding the entire sequence at once. I mean, they're with respect to the word good, it's not feeding in I am separately and then because I saw my friend separately. It's just feeding in the entire sequence at once, and they're calling it bidirectional because both aspects exist. So it's a misnomer. But I mean, it's only very important when you're applying these concepts. Otherwise, it's not really a huge deal. I know I talked about a lot this class, so for the next couple of minutes, I would love to field any questions that you may have. And after that, if you have any specific questions, you can feel free to talk to me. My email is over there. So, but however, any questions that I can answer about anything that I taught today, and in general as well, so I can help as much as possible. Yes, please.
So the same question I always ask about natural language processing. How do you define better, right? Or accuracy, or
absolutely great question. Yeah.
Is it blue score or something, or how do you know that
I actually didn't talk about blue score, but blue score essentially is a way of measuring how good the translation is. That's all. That's now better. Actually, it's weird because now in order to compare how BERT compared is that use a model with a similar parameter size as GPT. So it looked at similar parameter size models. It added just one layer, like how they both did, just one output layer, and it made a classification. It looked at the accuracy. It commented accuracies for similar parameter counts. So because the thing that's changing is the algorithm, not really like anything fancy.
What was being classified? I'm sorry.
Any different tasks. I mean, they have different tasks that they're associated. So it
So
depends
it's
on
not the translation, the quality of the translation. It
because
is.
it's only half of it. Now, if you think about it, you're not translating sentence A to sentence B. You're cutting it in half. You have sentence A and you're generating a representation. And GPT is
Okay, and how well did, it's like an autoencoder kind of thing, right?
It's like a what?
An autoencoder?
Yeah.
Okay.
It's very similar to autoencoders.
All right. So that I get. The blue score, I'm still.
Blue score is kind of weird. That's why I didn't go over it too much. Okay, any other questions that I can answer? For Rafi?
Could you just summarize in 1 second, in one sentence, what is a transformer?
Transformers. A contextualized way in order to get from sequence A to sequence B. So you context, essentially using the meanings of the previous words in order to get from some sort of input and transform it into some other valuable output. That's essentially what it is. I hope that helps. Okay, I think we are done for the day. Thank you so much for coming to this class, everybody. I really appreciated it. I did try to fit in a lot of concepts in a short amount of time. I do regret that, but obviously my email is over there, kachu11@gmail.com. And please feel free to email me or send me a message on Meetup. And Vinicius is there as well, the other coding. He's also very smart and knows all this stuff. So anyways, as I said, thank you, and I hope you have a great rest of your day. This, by the way, does conclude our NLP session. So this is our last class, and I don't know what exactly is coming up next, which you'll find out on the Meetup page. So it'll give you more information. Okay.
Tough life.
Okay, I'm working now on projects, so that's good. I'm trying to get ready for a pitch tomorrow. It's a bank. It's a big, huge financial institution.
Oh, yes, absolutely. Thank you.
What is it?
Yeah, I gave a workshop with that.